Hi and welcome to video 1 Trigonometry. In this video we're going to review basic right angle trigonometry, we'll cover some examples and we might talk a little bit about how trigonometry relates to the similarity concepts that you covered in the past. You'll note here that this is a review. If you've not learnt trigonometry before, well there might be other videos that are more suitable for you. So, first of all I'm going to look at this diagram over in the top right hand corner. Now this is a standard triangle. It has a right angle at angle B. And it has an angle marked here which is theta. That symbol is a Greek symbol, pronounced theta, and spelt like that. Now you'll notice here that we've identified some sides. We call this side the hypotenuse, we call this side the opposite, and we call this side the adjacent. Now the opposite side is always opposite the angle. And the angle in this case is theta, so the angle of reference. The hypotenuse is always opposite the right angle. Or it's the longest side. In a right angle triangle, the hypotenuse will be the longest side. The adjacent, therefore, is the one that's left. And that's how I look at it. But of course, adjacent also means next to. So the adjacent is next to the angle. So keep that in mind when you're labelling your sides. Now in this triangle, if we have a quick look, I can build up the concept of similarity. And you will have seen this type of similar triangle set before. So let's say we had that line there. And I call this E and D. The idea behind trigonometry is that the ratio between a pair of sides is the same no matter how big the triangle for equivalent angles. So let's say this angle theta, whatever it is, the relationship between the adjacent side and the opposite side, so let's say opposite divided by adjacent, will be the same for any size triangle as long as the angle we're talking about is still theta. It's still the same size, in this case about 30 degrees. And that's the idea, that's where it comes from in similarity. And when you've done your similarity concept, you've used that ratio relationship to actually calculate missing sides. And so the same will hold here. So now I'm going to move down to the work that we have in the bottom left-hand corner. And you'll notice these trig ratios. And you should have seen these before. And we have a sine function, a cosine function, and a tangent function. So sine, S-I-N-E, shortened to sin, but pronounced sine, is opposite over hypotenuse. So that's the ratio between the opposite side and the hypotenuse. Cosine, shortened to cos, is the ratio between adjacent and hypotenuse. Adjacent over hypotenuse. And then tan, which is tangent, is opposite over adjacent. And you may remember, or you may not have seen, the really simple way of remembering SOH, CAH, TOA, fairly common, pronounced Sokotoa way of remembering sine equals opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. And you'll see here a diagram to represent that. Typically as we move forward, I'll be calling this H, this O, and this A. So let's have a look at some quick examples. So example 1 first of all. 34 is our theta, it's our known angle in this case. This means that 94 is opposite, and our x is our adjacent side because directly opposite the right angle is our hypotenuse. And we don't really care about the hypotenuse, we don't want to know it, and we don't already know it. So we're going to work with an adjacent and opposite ratio, which in this case is tan. So we have tan 34 is equal to opposite 94 over adjacent x. I'll rearrange this equation by multiplying by x. And I get x tan 34 is equal to 94, and then I divide by tan 34, and I get x is equal to 94 divided by tan 34. I'll put this into my calculator very carefully to make sure that my calculator is set in degrees, and this will give me an answer of 139.36 kilometres. And this is reasonable. 94 is opposite the smaller angle because the sum of the triangle is 180 degrees. Therefore, this angle will have to be 56 degrees. So I expect x to be larger than 94, but not that much larger. So 139.36 fits the bill. Example 2. In this case, I'm working with my angle. Theta is here. I have the adjacent side and I have the hypotenuse. So adjacent hypotenuse is the cosine ratio. Cos 72 is equal to adjacent, which is x, over hypotenuse 39.7. Now I calculate that by rearranging first, multiply by 39.7, and I get 39.7 cos 72 is equal to x, and of course that means that x is equal to 12.268 centimetres. Now it's probably important to note here, I've done 2 decimal places in the first example and 3 in the second example. Realistically, there's no set defined procedure here. If the question identifies a number of decimal places, then use that identified number. Otherwise, if the context is something where it's really important to have accuracy, such as a lot of chemical context or architectural context, then you will have more, or you might just do something suitable. 2 decimal places really should be the minimum though. Example 3, finally, I have the angle, I have the opposite side, and I have the hypotenuse. I don't know the adjacent side, and I don't want to know the adjacent side. So in this case, this is a sine ratio. Sine theta is equal to 2.5, which is opposite, over 5.2, which is adjacent. Now how do we deal with the sine theta? This is like any normal equation. We want to unwrap the unknown value, which in this case is theta. So I do sine inverse of both sides. Sine inverse is the opposite to sine, and we'll remove the sine, giving me theta is equal to sine inverse of 2.5 over 5.2, which when I calculate this will come out as 28.736 degrees, or this can be written as 28 degrees, 44 minutes and 8 seconds if that's the way it's asked for. So there you have it. 3 quick examples on basic trig rules. SOHCAHTOA, a bit of an explanation for how that links to similarity, and that's pretty much everything you need to know for the basics.